Okay. So suppose there's an LCR series circuit like this connected to an AC source. You know how to derive the current equation. If the EMF equation is known to you, you can derive the current equation. It will be of this form. I is E naught by Z. And since the EMF function is sine omega t, current function will be sine of omega t plus that phase constant that you get from the impedance triangle. Okay. Based on current, you can write the expression for voltage across the resistor, capacitor, and inductor. That also we had done in the last class. Now consider something like this. Suppose an ammeter is placed in this branch. What does an ammeter measure? Generally, what?
All currents.
Galvanometer is for small currents. Ammeter is simply for current. Okay.
Oh, yeah.
Now, in this case, what we have is an alternating current. Okay, the current is of the form I is equal to I naught multiplied with an oscillating function. Okay, whether it is sine or cos, doesn't matter. I naught multiplied with an oscillating function. Then in this case, what reading will the ammeter show? Does it show peak value? Does it show current at that particular moment? Or does it show the average current? Does it show the RMS current? What do you think it indicates?
The average current,
What is the average of the sine function?
uh, pi by, no, 2 by pi, 2 by
See,
pi.
2 by pi is only for positive half cycle, but this current won't stop after executing the positive half cycle. No, it will keep oscillating up and down. So on the
Oh,
whole,
yeah.
what will the average be over a long duration? The current will be positive for some time and negative for some time, and it will keep repeating that. Then what is the average value of current?
0, sir.
Zero. Then do you think the ammeter will show zero reading if you connect it to an AC circuit?
No, sir, it won't show 0.
No, it won't. It won't. Okay. And see, the voltage that we get in a household power circuit, okay, is an alternating voltage only. Now, most of the electric or electronic devices that we use, if you observe their adapters or if you observe the ratings written on them, mentioned on them, you will see a voltage of 220 volt mentioned there. And frequency also they'll mention 50 hertz. Now, what we get is an alternating EMF, alternating voltage. But they but on the device, whether it's a bulb or you can look at your mobile charger also, on that in it'll be printed, okay, at what ratings it can be used. So they mentioned 220 volt as the voltage at which it can be used. What is this 220? We get an alternating voltage, but they mentioned a constant fixed value of voltage. What do you think this 220 is? Okay, this is actually the rated values are actually the RMS values. Now, what we get in the household power socket is an alternating voltage, alternating EMF. Its RMS value should be 220 volts at max. That is what the rating on the device means. Similarly, they'll even mention a current value. If you see the mobile adapter, it will be written 1 ampere, 1.2 ampere, or maybe 0.5 ampere. They'll mention a fixed value of current. But we know it's an alternating current. Okay, alternating EMF produces alternating current. Then what do they mean by the fixed value of current they indicate? It's the RMS value of the current. And that is what ammeters and voltmeters measure in an AC circuit. Okay, very important thing to remember, because in exam problems, they'll directly give you a voltmeter somewhere and ask you what is its reading. Okay, for example, if a voltmeter is fixed across the resistor, let's just call it V. They'll ask you what is the reading indicated by the voltmeter. Now you know the EMF across the resistor will be alternating. So average value will be 0. But in an AC circuit, when they ask reading of voltmeter or reading of ammeter, they're actually asking the RMS values, effective voltage, effective current. Okay, that is what you are supposed to answer. Okay, let's solve problems based on all this. Assume the resistance is say 30 ohms, XC is 60 ohms, and XL is 20 ohms. And the EMF as a function of time, let's say something like this, 200 sine 100t. Okay, 200 sine 100t. First, write the current as a function of time and then derive voltage across the resistance, voltage across the capacitor, and voltage across the inductor as functions of time. Okay, let's quickly recollect how to do this. We had discussed this in the beginning of yesterday's class or last class. If you know the current equation, okay, suppose current through the resistor is given by this equation, then its voltage can be written like this. Peak value of voltage will be I naught into R, and resistor keeps the current and voltage in the same phase. So whatever phase the current function has, same phase you will copy. Next, peak value of voltage across the capacitor will be I naught into XC, because I naught across the capacitor is V naught across the capacitor divided by XC. We had discussed all this. So V naught will be I naught into XC. Similarly, for the inductor, it will be I naught into XL. And you know what to do with the phase. Capacitor makes current lead, means EMF will be lagging. That's why minus pi by 2. Voltage will be lagging. Inductor makes current lag, means the voltage will be leading. So plus pi by 2. Okay, that way, if you know the current equation, you can write the voltage equation. So I want you to apply all this and solve this problem now. Make it fast.
But I'm not getting how to do this.
Okay. Tell me, how will the current function be? I mean, general equation of the current, AC current.
Where I not sine omega t.
But see, you have to, yeah, I naught sine omega t represents an alternating current. That's okay. But based on EMF equation, how can you write the current equation? Like the EMF equation you have here is of the form E naught sine omega t, right? E naught is 200. Sine in place of omega, you have 100 into t. And it's applied to an LCR series circuit. Then how do we write the current equation? Listen, it will be of this form. E naught divided by impedance, total impedance of the circuit, sine omega t. Whatever is the phase of the EMF function, write it as it is. Plus some extra phase you will get. That extra phase and this Z value we have to calculate. Okay, Rishi, keep this in mind. So to calculate these, we can use the impedance triangle, or if you remember the formula, you use the formula directly. Z is calculated as, can you tell me the formula for Z in terms of XC, XL, and R? Anyone?
So can you repeat your question?
The formula for Z in terms of XC, XL, and R. Okay, looks like you didn't really go through the last class. Let it be. It will be under root XC minus XL whole square plus R square. So if you substitute all that, XC minus XL, 60 minus 20 is 40 squared, plus R is 30 squared. Root for 40 square plus 30 square is 50 ohms. That's the total impedance of this circuit. So we got Z value, and then to calculate the phase constant phi naught, you can use the formula tan phi naught is equal to XC minus XL. Here XC minus XL, 60 minus 20 is 40 divided by R. R is 30. So tan phi naught is 4 by 3. So you can say phi naught is 53 degrees, or simply write tan inverse 4 by 3. That's all. That way we get the current function based on the EMF function. So EMF is 200, peak value of EMF is 200, Z is 50. In place of omega, we have 100. So sine 100t plus tan inverse 4 by 3. I'm writing it as 53 degrees. Actually, it should be written in radians. So let's keep it tan inverse 4 by 3 itself. Okay. 200 by 50 is 4. So current effectively becomes 4 sine 100t plus phi naught. Tan inverse 4 by 3, I'm keeping it as phi naught. Rishi, is this part clear?
Yes, sir.
Pradyum, did you understand how to get the current equation from the EMF equation? No response. Okay, fine. Now that is the current that flows in this loop. And we know that in steady state, the current should be same everywhere in a given branch. So the same current flows through the resistor, capacitor, and the inductor. So we know the current in all of them. The next thing you were asked to find out is the voltage across each element. Okay. This is the current equation that we'll be using. Rishi, can you tell me how to write the voltage across a resistance if you know the current equation?
Sir, I naught XL sine phi.
XL is for inductor. Okay.
Yeah, sir. XC. No, XR.
There's no XR, it's only R. Okay.
Huh.
Huh. So let me write it here. If I is given as I naught sine something, let's say sine phi. Let's call the total phase as phi. Okay. Then voltage across the resistor will be I naught R, and resistor will keep voltage and current in the same phase. So whatever is the phase of the current function, take it as it is for the voltage function. Okay. Did you understand or not?
Yes, sir. Understood.
Okay. In this problem, the resistance given was 30 ohms. So now tell me the voltage equation, voltage across the resistor. Uh, Like use this formula as it is.
There will be 4
Resistance is 30 ohms.
4, yeah. So which is 120 sine 4 by
Ah,
3.
tell properly why is it sine 4 by 3? Where did you get the number 4 by 3 from?
Tan inverse 4 by 3, sir, because
What did you do to the 100t then?
sir, oh, yeah, sir.
Okay. So I naught into R becomes 120, and whatever is the phase of the current function, same will be the phase of the voltage across the resistor. Okay, that phi naught is tan inverse 4 by 3. I'm not writing it. Is this clear? Yes or no?
Yes, sir.
Okay. Now tell me, what is the RMS value of the voltage across the resistor?
E naught R by Z.
E naught R by Z root 2. Okay, you remember the formula, that's fine. But see, Rishi, we are we have just found something. No, we found the voltage across the resistor as a function. Based on this function, you answer.
120 by root 2, sir.
That's all. Peak value divided by root 2. That becomes 60 root 2 volts. Okay. So in this problem, if let's say you are given a voltmeter across this resistor and you are asked what is the reading of the voltmeter, this will be your answer. You first have to derive the voltage function and then find out how much is the voltage across, RMS voltage across the resistance. That RMS voltage will be the reading of that voltmeter. Okay. Next, same in this XC is given as 60 ohms. Remember that. And now tell me the equation for voltage across the capacitor. Generally, you look at the right hand side. If I naught if I is I naught sine phi, okay, some variable current is there. How do we write voltage across the capacitor?
I naught XC sine phi minus pi by 2 because it lags by pi by 2.
Correct. Capacitor will try to make the current lead, means the voltage lag. So you'll do minus pi by 2. So apply that and tell me the expression for voltage across the capacitor here. You can see the current function. XC is given as 60. Based on that, you answer. How much is I naught?
Sir, it'll be 240 sine 100t.
Hmm.
5 is here.
Keep phi naught as it is. Okay.
Okay, so then it'll be 100t minus 4 by 3 minus pi by 2.
Okay. Okay, fine. So 4 is the peak current I naught multiplied with XC 60. I naught into XC becomes 240. 4 into 60. Sine whatever phase the current function has, take it as it is first. 100t plus phi naught. Phi naught is tan inverse 4 by 3. Let it be. To avoid writing that complicated term, I'm representing it by phi naught. Let it be minus pi by 2. That's all. That's the voltage across the capacitor as a function of time. And sine of theta minus pi by 2 becomes minus cos theta. So this can be written this way also. Voltage across the capacitor minus 240 cos 100t plus phi naught. You can write it like this also. Or in the options, it may be given like this also. Okay. Again, on the right hand side, you tell me How do you write voltage across the inductor if the current function is known?
I naught XL sine phi plus pi by 2.
Okay. Sine whatever is the phase of the current function plus an extra pi by 2. Do the same here. Tell me the voltage across the inductor. XL was given as 20 in this problem.
80 sine 100t plus phi naught plus pi by 2.
Plus pi by 2. Okay. So 4 into 20, peak value becomes 80. Sine of 100t plus phi naught plus pi by 2. And sine of anything plus pi by 2 becomes cos of that thing. So this voltage across the inductor can be written as 80 cos 100t plus phi naught. This way you can get voltage across resistor, capacitor, inductor separately. And then if you are asked what is the reading of the voltmeter, okay, you can tell. Like if the voltmeter is connected across the resistance, you have to tell the RMS value of the resistance voltage. If the voltmeter is connected across the capacitor, you have to tell the RMS value of the capacitor voltage. Similarly, inductor. So wherever a voltmeter is connected, if they ask you what is the reading of the voltmeter in an AC circuit, you have to get the voltage function first and then take its RMS value. Okay. And if you are given an ammeter in that circuit and you're asked current, you'll get the current function and tell the RMS value of current. That will be the reading of the ammeter. And there's one more thing you need to observe. Let's take this set of equations. If current equation is known, we can write voltage across resistor, capacitor, inductor. Okay. But observe the voltage across the capacitor equation. It's like sine phi minus pi by 2. As I said, can be written as minus cos. So minus I naught XC cos phase of the current function. And voltage across the inductor, sine theta plus pi by 2 or sine phi plus pi by 2 is simply cos phi. Okay. So you can write it as I naught XL cos phi. If you observe these two functions, okay, the phase of the voltage across capacitor is phi minus pi by 2. Phase of voltage across inductor is phi plus pi by 2. Tell me, what's the phase difference between VC and VL? One function has a phase of phi minus pi by 2. The other has a phase of phi plus pi by 2. What's the phase difference between these two functions? Pradyun? Yeah, how much is the phase difference between?
Sir, minus 1. So it'll be cos.
Okay. First, tell me what.
180.
Okay, tell me your final answer.
I'm not sure, sir. 1 second.
See, there's nothing much to do, Rishi. What do you understand by phase? Like in the current equation or EMF equation, which part represents the phase?
Sir, the uh, omega t plus phi. That
Everything
part.
that is there inside the sine function or the cos function, whatever is there inside that sine or cos bracket is what you call as phase. So capacitor has a phase of phi minus pi by 2. Inductor has a phase of phi plus pi by 2. I'm just asking you what is the difference between them. Subtract them.
Minus 1, sir.
Where are you getting 1 from when you
No, no.
subtract those two? Okay. Pradyun, your answer is correct only. Phi minus pi by 2. And you have to take the difference with phi plus pi by 2. You just subtract them. The answer will be pi. That's the phase difference between voltage across the capacitor and voltage across the inductor when they are connected in series. Now listen, phase difference of pi is an interesting thing. When two sinusoidal functions have a phase difference of pi, we say they are exactly out of phase with each other. What do we mean by being exactly out of phase with each other? Listen, if you observe, one of them is the minus cos function and the other one is the plus cos function. Okay. Now, when this becomes plus 1, because of the minus sign, this voltage becomes minus 1. Or when voltage across inductor reaches its positive extreme, voltage across the capacitor will reach its negative extreme. Okay. On the other hand, when this becomes minus 1, this voltage across capacitor will be plus positive extreme. So voltage across capacitor and inductor will be doing the exact opposite things. If inductor has positive voltage across it, capacitor will have negative voltage. If inductor voltage is increasing, capacitor voltage will be decreasing. Okay. So remember, in an LCR series circuit, you will always see that the phase difference between voltage across capacitor and inductor is pi. Okay. So if one has positive voltage across it, the other will have negative. They'll always be opposite of each other. Okay. And see, these two are opposites of each other. That's fine. In terms of phase, they are opposite. But exact value, if you see, the peak value of capacitor voltage is I naught XC. Peak value of inductor voltage is I naught XL. Had these two been equal. Okay. Let's discuss that condition now. If XC is equal to XL, then what happens is something interesting. Voltage across the capacitor is minus I naught XC cos omega t, and voltage across the inductor is I naught XL cos omega t, or cos phi. Let's write cos phi. Fine. If XC is equal to XL, it means this whole thing without the minus sign is equal to this whole thing. Means voltage across capacitor and inductor have the same magnitude, but they are of exact opposite signs. Then in that case, the sum of these two voltages effectively becomes 0. Okay, and why is this case interesting? If the sum of voltage across capacitor and inductor becomes 0, that means all the voltage you are supplying, okay, this alternating voltage that is there, all the voltage that you are supplying would be going directly to the resistor. If XC is equal to XL, voltage across capacitor will be exactly the negative of voltage across inductor. So the sum will get cancelled. That means all the voltage applied is directly given to the resistance. Okay, still, why is that interesting? Let's see. We have the formula for impedance. Like if EMF is of this form, E naught sine omega t, then current will be of this form, E naught by Z sine omega t plus phi, or phi naught. So the peak value of current is E naught divided by Z. Now the formula for Z is under root XC minus XL whole square plus R square. Now in an AC circuit, once the circuit is designed also, you can change XC and XL values. How? The formula for XC is 1 by C omega, and the formula for XL is L omega, where omega is the angular frequency of the EMF function. Okay, this value. If you change the frequency of the alternating EMF that you apply, you will effectively be changing XC and XL values. One of them will increase, the other will decrease. Then at one frequency, you can make them become equal. Okay, just by adjusting the frequency of the source voltage, you can make XC become equal to XL. Now what happens if XC becomes equal to XL? This bracket becomes 0. And if this bracket is 0, Z will be equal to R. Okay. That is the least possible value of impedance. If Xc is equal to XL, Z becomes equal to R. If Xc is not equal to XL, no, Z will be more than R, because this term will be non-zero. On the right hand side, you can see if this bracket, first bracket is non-zero, then the Z value will be more than R. Okay. But if Xc is equal to XL, Z will be equal to R. And this is the minimum possible value of Z. Okay. If Z is minimum, the peak value of current, therefore I naught is equal to E naught by Z, becomes E naught by R. Okay. Z is at its minimum. So I naught will be at its maximum. That means if Xc is equal to XL, you will get the strongest current in the AC circuit. Peak value of current will be the highest. Okay. This condition is what we call as resonance. Okay. When the frequency, or I should say angular frequency, when the angular frequency is adjusted such that the current in the AC circuit is the strongest, or I should say, I can say highest possible value, the circuit is said to be in resonance. Fine. So in an LCR series circuit, current will be maximum when Xc is equal to XL. Okay. So under that condition, we say the circuit is in resonance. And what is the formula for Xc? 1 by C omega, and XL is L omega. Keep the omega terms on one side and the other terms on the other side. You get omega square is 1 by LC, or omega is equal to 1 by square root of LC. So at this particular value of angular frequency, Xc becomes equal to XL. Okay, and remember, angular frequency can be adjusted by us because we are the ones applying the alternating voltage, E naught sine omega t. So we can make adjustments to that and automatically Xc, XL values will change. So at this value of omega, Xc becomes equal to XL. That means Z becomes R. R is the least possible value of Z. Okay. And if Z becomes R, the peak value of current becomes E naught by Z, that is E naught by R. So this is the maximum possible peak current. Okay. And this value of omega, 1 by under root LC, is called resonant. Okay, because at that frequency resonance is happening, no? So we call it as resonant angular frequency. Okay, let's discuss this point once again, resonance. Basically, in an AC circuit, the current equation will be E naught by Z sine omega t plus phi naught. So the peak value of current depends on the impedance of the circuit, Z value. And Z value in turn depends on Xc, XL and R. Now, in the AC circuit, when you build the circuit, a capacitor, an inductor, a resistor will be kept. You can't change, okay? You can't change C, L, R values. These cannot be adjusted. But the omega of the EMF that you are applying, okay, this value, the angular frequency of the alternating EMF can be adjusted by us. And when you adjust that, XC and XL will get adjusted. C and L won't change, XC, XL values will change. Okay. Now, when you change XC and XL values, you will indirectly be changing the Z value. And if you are changing Z value, it means you are changing the peak current in the circuit. So you can adjust how much current flows in an AC circuit by altering the frequency, by changing the frequency. Now, for one particular frequency, you will get maximum current. When does that happen? When Z is the least. And when will Z be the least? When the first bracket in that Z formula, this term, becomes 0, automatically Z will be minimum. When will that bracket become 0? XC should be equal to XL. Okay, XC equal to XL means omega should be 1 by root LC. At that much angular frequency, Z will be minimum, current will be maximum. That condition is what we call as resonance. Okay. Can one of you tell me how frequency is related to angular frequency? What is the relation between F and omega? How is frequency related to angular frequency?
Is it 2 pi f or something like that?
See, you should not do guesswork.
Yeah, I think it is 2 pi f, sir.
Okay, fine, fine. So time period is 2 pi by omega. So frequency is omega by 2 pi. So omega becomes 2 pi f. I'm asking you what is f? It will be omega by 2 pi. So the omega value at which resonance occurs is called the resonant angular frequency. The f value at which resonance occurs is called resonant frequency. Omega is called angular frequency. Omega by 2 pi is normal frequency. Therefore, resonant frequency becomes 1 by 2 pi under root LC. Okay. So for the previous question, like we took XC, XL values and all. Okay, without knowing L and this you cannot tell. Let it be. So if you know the inductance and the capacitance that are there in the circuit, you can tell what is the resonant frequency of that circuit. And see, at resonance, that is when XC is equal to XL, we know we get maximum current. Okay. And if current is maximum, more current flows through the branch, more power will get dissipated by the resistance. One of you quickly tell me, what is the formula for power dissipated by a resistance or resistor?
I square r, sir.
Okay. That is if the current is constant. What if it's a variable current? Power dissipated by a resistance. For constant current, it is I square R. What if it's a variable current?
Sir, we take the average of it and then
Average of what?
the power and then
Okay, that can be done. You have to write the current function, power function, then take its average. But you need to remember the definition of something called RMS current. When an alternating current is present, you take its RMS value. It will give you the power directly. Okay. You have to write the function, take its average and all, but instead you can directly substitute RMS value of the current. Okay. So at resonance, peak value is maximum. Okay. That means the RMS value of current, which is I naught by root 2, will also be maximum. And if RMS value of current is maximum, power dissipated will also be maximum. I RMS squared into R will be maximum. And last class we derived one formula for power dissipated. We wrote it as IRMS ERMS cos phi. Okay. This term cos phi is called power factor. Okay, I'll show you the impedance triangle. In the impedance triangle, what we do is we take resistance like this, R, we take a vector of magnitude R like this, and we take a vector of magnitude XC minus XL like this. And their resultant is what we call as Z. This is the impedance triangle. And this angle is called phi naught. Now from this triangle, one of you tell me, how much is cos phi naught? From the triangle. It's a right angle triangle. In a right angle triangle, how do you write cos of an angle?
So can you repeat your question?
Do you see the right angle triangle there? The impedance triangle?
Yes, sir.
Huh.
Yes, sir.
Based on the sides given uh, in the triangle, tell me how much is cos phi naught?
R by Z.
R by Z, adjacent by hypotenuse. Correct. So generally power factor is R by Z. At resonance, one of you tell me how much is Z equal to? Resonance means XC is equal to XL. If XC becomes equal to XL, what does Z become?
R square.
Z becomes equal to R. Then if Z is equal to R, that means the power factor cos phi naught, which is R by Z, becomes 1. Okay. Therefore, at resonance, power factor is 1. And 1 is the highest possible value of power factor that you can have. At any other angular frequency, non-resonant angular frequency, if you take, Z will be more than R. And if Z is more than R, power factor will become less than 1. So maximum power dissipation will happen at resonance. Okay. Let's solve one more problem. Just a moment. Suppose you are given EMF, something like this, 100 sine 100 pi t, or okay, let me change it a little bit. We'll take it as cos this time. Okay. And at this value of omega, we have fixed an omega here. Okay. At this value of omega, R will anyway be fixed always. Let it be 20 root 3 ohms. Let's say XC is 10 ohms. XL is 30 ohms. I want you all to calculate okay, first derive the current equation. Then tell me what is the average power dissipated? And also tell me the power factor in this case. Try. (20√23). How did you
I
get that?
think something
What's the formula for Z?
XC minus XL square plus R square whole root.
How much is XC minus XL?
10 minus 30.
Minus 20.
Yeah, which is 4. Then 20 root 3 square is 60.
20 root 3 whole square. It's not just 20 into
Yeah,
root 3 square.
that's it.
So XC minus XL whole square is 20 square plus R square is 20 root 3 whole square. You do this, how much does it become?
460.
What are you saying? 20 square itself is 400 plus 20 root 3 when you square, it becomes 400 into 3, 1200. 20 root 3 whole square is 20 square into 3.
Oh, yeah, yeah. Oh my God. Sorry, sir. My bad.
Root 1600. Z becomes 40 ohms. Okay, we got Z.
Sir, I got it. I'll do it. That's not it.
Okay, make it fast. Pradyun, any answers? If you have, you can share. It'll be better if you can unmute. Next time, like, just check your device once. Okay. The other thing left is phase constant.
Sir, I is 5 by 2 sine 100 t plus
Mm. Okay, tell me the formula for tan phi.
tan phi, XC
Yeah.
minus XL by R, sir.
You have to do that calculation. XC minus XL is 10 minus 30 divided by R is 20 root 3. 10 minus 30 is minus 20. So minus 20 divided by 20 root 3 becomes minus 1 by root 3. Any idea tan of what angle is minus 1 by root 3? 1 by root 3 is a well-known value of tan. Okay, tan 30 degrees is 1 by root 3. Tan of minus 30 degrees is minus 1 by root 3. So the phase constant this time becomes minus 30 degrees. 30 degrees is pi by 6. Okay, that's why I have given those values 20 root 3 and all. Let it be. Now we are in a position to write the current equation. I is equal to E naught divided by Z first. Okay, that's the peak value. E naught is 100 divided by impedance is 40. Then Rishi, when you gave the answer, you changed it to sine. I don't know why. EMF is written in terms of cos. Current also should be written as it is. Then you include the phase constant minus pi by 6. Okay. Till now, we always took EMF as sine. That's why we used to write current also as sine first. But if EMF is given as cos, you take the same for current function. Okay. And then you just adjust the phase. Phase means whatever is there inside the bracket. This function cannot be changed. Just adjust what's inside the bracket. Okay, 100 by 40 is 2.5. Then current effectively becomes 2.5 cos. The rest of it can be kept as it is. Okay. Rishi, is this clear?
Yeah, sir. Calculation mistake.
Okay. And now you tell me one small conceptual question. When current passes through these elements, resistor, capacitor, inductor, which of them dissipates power? Means which of them releases heat?
Resistor, sir.
Only the resistor. Capacitor, inductor just store energy inside them and give it back to the circuit itself. Resistor, on the other hand, converts the electrical energy into heat. So that's the only one dissipating power. Okay, fine. Tell me the average power dissipated now. Formula first.
The formula is IRMS, then ERMS, and cos phi.
You can do all that. Otherwise, see, you know resistor is the only one dissipating power. And power dissipated by a resistor can simply be expressed like this also, IRMS square into R. Okay, they're all the same.
Oh, yeah, sir, yeah.
Huh. Now tell me how to get IRMS.
Sir, it's 2.5 by root 2.
Peak value divided by root 2. Okay, when you square it, it becomes 2.5 whole square divided by root 2 whole square. 2.5 whole square is 6.25 divided by root 2 whole square is 2. And the resistance in this problem is given as 20 root 3. Okay, let it be. You don't have to simplify, or maybe you can simplify it a little bit. 6.25 into 10 is 62.5 root 3 watts. Assuming everything is in SI units, this is the average power dissipated by this circuit. Okay. And what's the formula for power factor? Cos phi naught.
R by Z.
R by Z. R is given as 20 root 3 divided by, we got Z as 40. So the power factor is root 3 divided by 2. Or you could have answered that based on this angle also. You know phase angle is pi by 6, 30 degrees. Cos 30 degrees is root 3 by 2. That way also you will get the answer for power factor. Okay. So see, you are given XC, XL values here. They are clearly different, which means the circuit is not in resonance. And when the circuit is not in resonance, the power dissipated is not the maximum possible value. Okay. This is not the maximum possible average power. We can increase this further also by changing XC, XL values. Fine. Now we got the power dissipated. Basically, this 62.5 root 3 is the rate at which energy is being lost from this circuit. Okay. Who is supplying energy to the circuit? What is driving the current here? What is providing electrical energy? Rishi, generally in circuits, where does electrical energy come from? It comes from the battery. Okay, just I don't know why it got disconnected. Are you able to see my screen?
Yes, sir.
Okay. So tell me, what is supplying energy to the circuit? Or this resistor is dissipating heat. So it's giving out energy. That's fine. Where is it getting the energy from to give out? The energy is supplied by the source of EMF, the battery or the AC source. Okay, in this case, it's an AC source. Okay. Now, assume there was a DC source, a battery maintaining a constant voltage. Let's say the voltage is V and a current I passes through it. Okay. So if a current I passes through a voltage V, the rate of energy loss, or say the battery will keep on losing energy. It supplies energy to the circuit. So the battery loses its own energy. The rate of energy lost by the battery, or maybe I should say pumped by the battery. It's pumping energy into the circuit. Is simply I multiplied with V. Okay. Because generally when a charge dq passes through a potential difference V, then it gains or loses an energy of V into dq. That's the energy gained or lost when a charge q passes through a potential difference. We had discussed this before also. Simply divide by dt on both sides, small amount of time. Du by dt is the rate of gain or loss of energy, and dq by dt is current. So voltage multiplied with current is the rate of loss or gain of energy. A battery will be losing energy, so you can say the rate at which a battery pumps energy into the circuit is current flowing through the battery multiplied with the voltage of the battery. Okay. The same idea can be used in alternating circuits also, alternating current circuits. Now let's consider this question itself. The source EMF was given. Okay, follow this carefully. The source EMF was given like this: 100 cos 100 pi t. It's an alternating EMF, alternating voltage. Okay, and we got the current like this. I is equal to 2.5 cos 100 pi t minus pi by 6. Okay. So we know the source voltage and we know the current in the circuit. The same current will be passing through the source also, that AC source that is there. Okay. What I mean is, whatever current passes through the resistor, capacitor, inductor, the same current goes through this alternating EMF source. So the rate at which the source delivers power, rate of pumping of energy into the circuit, will be the voltage multiplied with the current. If you multiply them, 2.5 into 100 is 250. Cos 100 pi t is one function. Again, cos 100 pi t minus pi by 6 is another function. This is the rate at which energy is being pumped into the circuit. Okay. Tell me, will all the energy pumped into the circuit get dissipated?
No, sir.
No. Okay. Because the capacitor inductor can store some of the energy, right? So the rate of pumping of energy need not be equal to the rate of dissipation of energy at a particular instant. Okay. Let's say at a particular instant, energy is being sent at a rate of say 10 joules per second. Okay. Suppose the capacitor is storing 2 joules per second, inductor is storing 4 joules per second, 2, 4, 6. The remaining 4 will be dissipated by the resistor. Resistor cannot store energy. So rate of delivery of energy is not always equal to rate of dissipation of energy instantaneously. But average value, if you see, as the cycles keep on running, the capacitor stores energy and gives it back to the circuit, stores energy, gives it back to the circuit. Inductor also does the same thing. Resistor keeps on dissipating energy. Source keeps on pumping energy. Okay. Now, if the source is keeping on pumping energy and the resistor is continuously dissipating, if you average it over a certain time interval of many cycles, then the average energy pumped in will be equal to the average energy dissipated. Because capacitor energy, inductor energy don't go on increasing. They increase, decrease, they increase, decrease. Okay. So they'll be maintaining a fixed value of energy, average value. So if input is continuously being given and capacitor inductor can only store a certain amount of energy, then output will be continuously happening. Outflow will be continuously happening. So at a particular instant, input power need not be equal to dissipated power. But if you average it over many cycles, then input power will be equal to dissipated power. These are some of the like finer points in this chapter. They may not ask you that deep also. So now you know how to find out voltage across any element. You know that the phase difference between voltage across capacitor and voltage across inductor is 180 degrees or pi. That means they'll be out of phase. If one is positive, the other will be negative. And if Xc is equal to XL, the positive and negative will cancel. All the voltage will go to the resistance itself. And in that case, the power dissipated will be maximum. Okay. Now, Rishi, you tell me in an alternating circuit like this, suppose a voltmeter is connected across the capacitor inductor combination. How will you tell the reading of that voltmeter?
Sir, first we'll calculate VC and VL,
Okay, good.
and then can we sub? No, but that won't make sense.
Why will it not make sense?
Like
They are all,
subtracting both of them.
they are exactly out of phase. No, if one is positive, the other is negative, you
Oh
will
yeah, yeah,
have to
yeah.
subtract. Okay. So effective voltage across capacitor inductor combination. See, effective voltage means RMS voltage. You will take it as VC RMS minus VL RMS. Okay, you take their RMS values and subtract. Okay. Since they are exactly out of phase, you can do that. What if you are asked to do something like this? Effective voltage across resistor capacitor combination.
So can you repeat your question?
What if you are asked to find out the effective voltage across the resistor capacitor combination?
Oh, then same thing, sir. First we find VR, then VC, and then subtract.
You can't subtract because
Oh,
VR, VC are not exactly out of phase. Okay, they only have a phase difference of pi by 2 between them. Means when one is 0, the other will be maximum, or maybe when one is 0, the other will be negative maximum. So they are not exactly doing opposite things. Okay, fine. We'll discuss all this. Suppose you know the current function. Okay, in an AC circuit, you can write the current function now. Impedance and phase angle phi naught, if you calculate, you can write the current function. Let's say that part is done. And you got the current function like this. I naught sine of some phase. I'm taking it as a sine function. Rishi, tell me, what is the expression for voltage across the resistance?
sir, I naught R sine phi.
Correct. What's the expression for voltage across the capacitor?
I naught XC sine phi minus pi by 2.
Good. Okay, we have expressions for VR and VC. One of them, let's say, has a peak value of V1. Assume the resistor voltage peak value is V1, that I naught into R, I'm taking it as V1 sine phi. Phi is actually a function. You may have omega t here or omega t plus pi by 2, something like that. It's a function of time. Okay. Remember that it's not a fixed value. And the capacitor voltage, let's write it as V2 sine of phi minus pi by 2. We want the resultant of these two voltages now. Okay. So the effective voltage across resistance plus capacitor combination will be VR plus VC. So you need to add these two functions. V1 sine phi is one function. V2 sine phi minus pi by 2 is the other function. How do you get the sum of these two? You can't directly add them and say V1 plus V2 into something. Okay, one is sine phi, the other is sine phi minus pi by 2. So little bit of mathematics here. If you want to express this as a single term, okay, we have two oscillating functions here. This is one oscillating function whose phase is phi. This is another oscillating function whose phase is phi minus pi by 2. We need to combine them and make it a single function. How do we add two sine functions or one sine, one cos? Such additions also can be done. We'll discuss this case first. So how to add two sine functions? Treat them as vectors. First one, V1 sine phi. So draw a vector of magnitude V1 at an angle phi. Phi could be any angle, we don't know. Okay. Okay. Yeah. Draw a vector of magnitude v1 at an angle phi. Let's say you are taking angles with the x-axis. Draw the next vector of magnitude v2 at an angle phi minus pi by 2. From phi, if you subtract pi by 2, the other vector will be like this, v2. Now you want the effective voltage of these two, right? The effective voltage when you add these two sine functions will be the resultant of these two vectors. So this is the effective voltage, you can say. And because these two vectors are perpendicular to each other, see, one angle is phi, the other angle is phi minus pi by 2, means the difference is pi by 2, 90 degrees. These two vectors are perpendicular to each other. Because they are perpendicular, the resultant will be root of v1 square plus v2 square. Okay. Therefore, that's the effective voltage between the resistor capacitor combination. Because the phase difference between them is pi by 2, the resultant will be root of v1 square plus v2 square. Got it? Now, this idea is from mathematics. I don't want to teach you this. I mean, I don't want to explain how you get this, but this is how you add two sine functions. First sine function, whatever angle it has, at that angle you draw one vector. The other sine function, at whatever angle it has, you draw one vector. The sum of those two sine functions, the effective value, will be the resultant of these two vectors. Okay. We'll solve problems, you'll get used to it. Now, we know VC function. VC equation we know, and we can write the VL equation also. It's quite easy for you now. It is I naught into XL sine phi plus pi by 2. Okay. Let's take this as V3 sine phi plus pi by 2. Okay. Now, suppose you are asked, what is the effective voltage across capacitor inductor combination? You know it is VC minus VL. You know you have to subtract, but I'll just explain that in terms of that vector diagram. One second. Yeah. So we have two vectors here. I mean, we have to consider them as two vectors here. One of them is of magnitude V2. The other is of magnitude V3. And what is the angle between these two vectors? One is phi minus pi by 2. The other is phi plus pi by 2. Means the angle between them is 180 degrees. The difference between them is pi. So if you take, okay, let's assume some angle phi first, imaginary angle. Then phi minus pi by 2 would be like this. So take V2 vector this way. And phi plus pi by 2 would be like this. Take V3 vector like this. They are exactly opposite to each other. And if two vectors are exactly opposite to each other, then what is the resultant? It will be root of V2 minus V3 whole square. If V2 is bigger than V3, you write V2 minus V3. If V3 is bigger than V2, you write V3 minus V2. So it all depends on which one is dominant. Okay, that's why the effective voltage across the capacitor inductor combination will always be the difference between their voltages. Okay. So using these ideas, you can tell the effective voltage between resistor capacitor combination, capacitor inductor combination, maybe resistor inductor combination also you can tell. Okay, we'll stop it here for now.
Sir, can you show the last part?
Okay.
I just want to note it down.
This one.
Yes, sir.
Okay. I'll send you the notes anyway.
Yes, sir.